So it's a pleasure, as always, to welcome Eric Doka back to the group. And today we're going to hear about some new methods for computing von Neumann entropy and Renyi entropies. So let's make sure we're all muted and everything, but people can jump in with questions. It's a small enough group. Just unmute yourself. And we will also, of course, have some time at the end for discussion. So without further ado, welcome, Eric.
Okay, well, thank you very much, Cliff. Thanks for inviting me. So I think this is a day that you will never forget in your life, although perhaps not because of this seminar. I have to kill this admit. Okay, yes.
We'll do it, but
we'll do it?
sorry,
okay.
It keeps popping up on your screen.
Okay. So basically this work is based on a paper of the summer with Phi Dong and Shihong Wu at UCSB. And it's very heavily based on earlier work, some beautiful papers by Calabrese, Cardi, and Tani of about 10 years ago. And I'll explain the connection as I go on. So you're all familiar with the von Neumann entropy. If I consider it for a thermal density matrix, then the von Neumann entropy simply reduces to the thermal entropy you're used to from thermodynamics. And you can evaluate it in terms of the partition function. And if you're dealing with a quantum field theory, then the partition function is given by a standard functional integral, which you may or may not be able to do, but you can certainly work on it in perturbation theory. Now, on the other hand, you can also have a density matrix which does not arise from a thermal situation or thermal ensemble. For example, when you have the density matrix associated to a subsystem of a full quantum system. So for those kinds of density matrices too, you can define the von Neumann entropy, as we will see by the same formula. And the von Neumann entropy provides a measure for the entanglement of the subsystems with their complement in the whole system. But here, contrarily to the case of the thermal density matrix, it is not generally known how to evaluate the von Neumann entropy in a quantum field theory. The one exception is when there is a modular Hamiltonian known. Then, of course, you can essentially use the same methods as in the thermal case. And this was done extensively about, I don't know, 8 years ago or something by Cassini and Huerta. But that's a very special case. So in the absence of a direct method in quantum field theory, what's often used is the replica trick in terms of Renyi entropies. And I'll explain that in detail, but essentially the replica trick evaluates several copies. So their copies are labeled by an integer, a positive integer n. And then somehow the trick is to analytically continue from these integers to a real value and then evaluate the von Neumann entropy by differentiating there. So this goes under the name of the replica trick. It's very well established in condensed matter physics. But it is also known that it sometimes gives the right answer and sometimes doesn't. So here, the goal of this work and of this talk is going to be to develop a more systematic method in which, so to extract the von Neumann entropy from Renyi entropies without having to invoke this funny analytic continuation, which is characteristic of the replica trick from integers to the complex plane. So as an application, I'll show you some simple analytical calculations and then also some numerical calculations to show how to apply it, and in fact that it does work to a large extent. So let me just start with the beginning. So a density matrix, rho, in some Hilbert space for a quantum system is a self-adjoint operator. It's positive. You normalize it so that the probabilities and sum up to 1. And so because of these properties, you can diagonalize it in some orthonormal basis n of the Hilbert space in the following way. So rho is a sum over alpha, p alpha, and then these diodes. And I'll assume that different alphas are orthonormal to one another. And so because of positivity, these p's are positive. And because the trace is 1, they all have to be less than 1. So they're between 0 and 1. And you can think of them as probabilities, classical probabilities for the superposition, incoherent superposition of the states, or of the density matrix of pure states. Okay, so now the case we're going to be mostly interested in is when we associate a density matrix to a subsystem. So the setup is that we take the Hilbert space to be the tensor product of two Hilbert spaces, HA and HB. And to keep things simple, let's take a pure state in the large Hilbert space. And if we now limit observations to observables that live only in the subspace, let's say HA, then those expectation values can be reformulated in terms of the reduced density matrix, which I'll call rho A, and which is the trace over the complementary Hilbert space HB of the dyad for the pure state. And here I'm again assuming that the pure state is normalized to 1. Okay, so you all, I think at some point encountered this. Most of the time afterwards here, I'm just going to denote rho A by rho so as to not trail the subscript. But the idea is in this talk is really that rho comes from a subsystem. So now, from the point of view of the subsystem, the state that you obtain for A is not pure anymore, it's entangled. And you can have different measures of the entanglement. The simplest one is probably the Schmidt number, which is the rank of this matrix rho. And if the rank is 1, that's true if and only if rho corresponds to a pure state. That makes sense from this decomposition. And then if rho is larger than 1, then the state is actually genuinely entangled. Of course, this is a very rough measure of entanglement because you could have a pure state and add a very small admixture of another pure state with a p alpha of 10 to the minus 10 or something. Then the Schmidt number would be 2, but actually it's incredibly close to a pure state. So instead, the von Neumann entropy is defined in this way, as you know. So it's minus the trace of log of rho log rho, which in the above variables is p alpha minus p alpha log p alpha. So of course, since the p alphas are between 0 and 1, log is actually negative, and so this is a positive number, so that's good. So the entropy is positive for all rho, and it's 0 if and only if rho corresponds to a pure state. So it also provides a measure of entanglement of the state, but this one can assume real values. And so it's actually much finer. If you have 1p, which is very small, then in fact the von Neumann entropy is then also small. If you have a thermal distribution, then the von Neumann entropy simply reduces to the thermal entropy. And I've written down some formulas here that you all, of course, know about. And so More generally, if the distribution is associated with a modular Hamiltonian, then actually you can use your thermal formulas. But that's true only for very special systems, in particular when the Hamiltonian is the boost operator, for example, for a Rindler space. So that's the definition of the von Neumann entropies, entropy. Now, Renyi entropies are defined as follows. So in fact, there's not a single Renyi entropy, but they're labeled by integers from 2 to infinity. And they're given essentially by the trace of rho to the n, except that the way Renyi define things, there's in fact a log, and then there is a prefactor of 1 over 1 minus n. So in the case where n is equal to 1, the trace is equal to 1, and then the log is 0, so this is indefinite. But for all other values of n, this is a positive number. So they also give a measure of entanglement, but they do not reduce to the thermodynamic entropy, of course. The formulas are completely different. And also, while the von Neumann entropy obeys these properties, general properties of entropy, of additivity and subadditivity, Renyi entropies do not obey these relations. So now I'm going to specialize to a field theory. The considerations before were all very general. So now I want to go to a field theory. In fact, I'll take a two-dimensional CFT, and I'll take it to be unitary. And so what I want to do now is, within this context of this simple CFT, look at what can be evaluated and whether in particular the von Neumann entropy can be calculated. And if so, then how can it be calculated? So for this reason, I take essentially the simplest system, which is a two-dimensional CFT. In fact, we can even take a free boson or a collection of free bosons. Tau is Euclidean time, X is space, and we'll assume some Hamiltonian and some Lagrangian as usual. And so then you know that the matrix element of the Boltzmann operator between two field configurations, field eigenstates, is given by the path integral, functional integral. So phi1 here and phi2 are functions of space only, and so the functional integral representations, you integrate over all phi, the integral over the Euclidean Lagrangian, and then from 0 to beta, where beta is the inverse temperature, with boundary conditions. The boundary condition being that the field, when tau is equal to 0, is equal to phi1, and when tau is equal to beta, is equal to phi2. So that's analogous to the evolution operator if beta had been imaginary, but here it's of course real. So the partition function, as usual then, is given by setting phi1 to phi2, and then functionally integrating over all the functions of x in this combination. Okay, so now let's set up a density matrix for a subsystem of the real line R, which consists of a union of disjoint intervals. So I've written it down here, or maybe more easy to see is this picture. And we're assuming that these intervals have no intersection, zero intersection. And so A here is this, and then B is a complement. And so from a field theory point of view, we're interested in looking at the density matrix, the reduced density matrix for functions that have support on A only. Okay. There's some music in the background, which is very nice, but so in the case of n is equal to 2, hi Itzhak. For the case of n is equal to 2, I made this figure here, so I'm going to assume just 2 disjoint intervals, and then the complement of that is this region B, which is formed by the union of the remaining 3 intervals. So how do we obtain the reduced density matrix? Well, we need to give the value of the fields on the intervals A, the intervals that make up A, and then we need to trace over the functions that take support on B. So that means that the functions phi at tau is equal to 0 and tau is equal to B on the part in B are identified with one another and then integrated over in these 3 regions. So that, in fact, will give you the reduced density matrix for the quantum field theory just on the intervals A. Does that make sense to everybody? If there are questions, please interrupt and ask. Okay. So now what can one compute? So this is the setup for the single density matrix and its matrix element within the fields, the field values on the intervals A. So what can we compute with this? Well, of course, for the von Neumann entropy, we'd like to compute the log of rho or the trace of rho log rho, but it is unknown how to take the log of this operator. Okay, that's a complicated operation which we don't know. On the other hand, what we can obtain is to take the trace of the nth power of rho, where n is an integer. And the way you do that, after all, the trace of the nth power is simply the multiplication of the density matrix rho n times, and then identifying the n's and tracing over it. So here I made this figure for the case n equal 3. And so we have again, for each rang here, we have again the picture of the previous page for a single density matrix. So you should think of this as a single density matrix. This is another density matrix, and this is the third. And so the operation of tracing over rho to the n means that we identify the functions on these intervals, separately the functions on these intervals, then integrate over them, and so on and so forth. And finally, the trace is gotten by identifying these guys, and then also summing over. Okay, so in short, while you cannot access the log of rho or the trace of the log of rho, you can access trace of rho to the end. If this was of course the picture for just space. If I make a picture of this in two-dimensional space-time, then the intervals A, I didn't give them a name here, but these are A, these two components make up A, actually become branch cuts. And so in a conformal field theory, you can then identify the branch cuts across different sheets and build up a higher genus Riemann surface from this. And again, in a CFT, you can produce these branch cuts. In this case, this is a third order branch cut. You can produce it by inserting a twist operator of degree of order n. So that's the two-dimensional picture of this. So in fact, this is why this was done in a conformal field theory, because in a conformal field theory, I have these twist operators, and I know how to handle this expectation value of the twist operators on a genus, an arbitrary genus surface. So how can we carry this out? So fortunately, all this was carried out a long time ago, 10 years ago, mostly in papers, initially by Cardy for a single interval, and then for two intervals by Calabrese, Cardy, and Tani. And so what do we have? So in fact, we can be a little bit, they did this a little bit more generally and consider the CFT with central charge C. So a little bit more general than a free boson. In the case of a single interval between x1 and x2, the expression for trace of rho to the n is simply the exponential of 1 over n minus n times y, where this variable y is the central charge over 6 times the log of the distance, the length of the interval, and then you need a cutoff. You need an ultraviolet cutoff. And the reason you need a cutoff is because basically your separation of the intervals A and their complement is done by a sharp cutoff in space. And so that introduces a UV divergence, which you have to cut off. So this formula it was derived by Cardy. If you have two intervals written like so here, then you have, first of all, a prefactor, which is reminiscent of the single interval prefactor, and in fact combines the contributions from the two intervals in this way with the cutoff, and again, the central charge C. But now it's multiplied by a function. And in a conformal field theory, that makes sense. There is, in fact, for two intervals, namely 4 points, there is a single independent cross ratio, x. And so in general, you can have a non-trivial function here, fn of x, which depends on the dynamic, depends on what the CFT is. It's not a universal function like we had here. Now, for a general CFT, you can't evaluate this fn exactly, but you can expand it in a limit where x is small. So that is basically the case where the intervals are small, the length of the intervals is small compared to their relative separation. You see that if x12 and x34 are small compared to x13 and x14, and so then this is a small number. So in this limit, you can in fact evaluate what fn is. And so I wrote the expression here. So it depends on x, okay? It depends on the index n for the Renyi entropy. And then it also depends on a number alpha and a number n. So alpha is alpha over 2 is the lowest operator dimension in the CFT other than the dimension of the identity, which is 0. So that makes sense, right? You're looking at the long distance effect between two intervals. It's the lowest dimension operator that will dominate that correlation function. N is the multiplicity of that lowest dimensional operator. That also makes sense. That will be multiplicative. And then the dot, dot, dot here stand for higher powers in X, which would involve higher dimension operators and so on and so forth. So this expression was calculated by Calabrese, Cardy, and Tani, and we will take it at face value. Any questions? Okay, so now this is all great. We now have the Renyi entropy, but we are interested in the von Neumann entropy. So how can we do this? Well, we have here a collection of Renyi entropies. So if the Renyi entropy were known not for an integer n, but actually for a real or complex version of n, which we'll call nu, near nu is equal to 1, if that were known, then you could obtain the von Neumann entropy, which is minus the trace of rho log rho, as the limit when nu goes to 1 of the Renyi entropy. And the reason for that is that if nu is close to 1, then rho to the nu is approximately rho and then plus nu times log rho. And the 1 is canceled by the log, and the other thing, the 1 minus nu is canceled here. So you would actually get this formula back. So of course, that's not at all what we're given. What we're given is trace of rho to the n when n is an integer. So what do? Well, the replica trick relies on, I'll put it in quotation marks, analytic continuation in n to a number nu in the complex plane. That's a non-trivial analytic continuation. You're used to analytic continuations where you know the function in some open set, and then there is a standard method for analytically continuing. So it's not even clear that this analytic continuation from integers actually exists. And if it exists, then the question is it unique, or are there several ways of doing this? So the second question here, is it unique? That's actually addressed by a theorem, a well-known theorem in complex analysis called Carlson's theorem, which says the following. If you have a function f of nu that is holomorphic in nu for the real part of nu larger than 1, so essentially in the right half plane, right half complex plane, and vanishes for all positive integers nu, and is bounded when over a real part of nu larger than 1 by an exponential where c and lambda are positive numbers, and satisfies this bound with lambda less than pi for the real part of nu equal to 1, then the function f must vanish for all nu. So the reason you have these bounds here is that there are, of course, a lot of functions that vanish on the real positive integers. For example, the sign of pi nu vanishes for all integers, in fact. However, it does not satisfy this bound because lambda in this case would be equal to pi, and that violates the bound. So basically, when you have the Renyi entropy sequence, in order to guarantee that the analytic continuation exists, you sort of have to know how to extend this formula to complex values of n and then verify whether this bound actually holds. Okay, well, let's see how this works. So suppose we look at the one interval case. Now, actually, the one interval case is very special because just by looking at it, it's completely clear that you can continue n to any complex number nu that you want. So actually, for the case of the one interval, here are the Renyi entropies, and you can take the limit when n goes to 1 without a problem, and you find this expression for the entropy for a single interval. And this formula was due to Cardy longer ago than that. Now, on the other hand, if you look at the expression for the two intervals, the prefactor, of course, is essentially the same nature as for the one interval, but this function fn, even in its expansion for small x, has a non-trivial dependence on n. The first factor is, of course, analytic, that's fine. But here we have a sum, and the upper bound of the sum involves n. The argument here also involves n, but it's really this sum that's a killer. How do you extend this to complex values of n? Well, actually, Calabrese, Cardi, and Tani, by a lot of trial and error and guessing, actually were able to find an analytic continuation that does the job, and it's given by this formula here. So given the complexity of this formula here, it's actually remarkable that you find something that's very simple. So going beyond this has not been possible using the replica trick. So the goal of this talk is what leads to this alternative method that Xi Dong and Shihong Wu and I came up with, and that is to avoid the replica method altogether. So we're going to assume that the Renyi entropies are known for all integers n, but not more than that. I'm not going to assume there's an analytic continuation. And from the Renyi entropy, it's essentially equivalent to know the trace of rho to the n for all n positive. So now the alternative method is actually incredibly simple. What you do is assemble these traces of rho to the n in a generating function with an auxiliary parameter z, complex parameter z. So the way you do that is you put them all in an infinite sum from 1 to infinity, z to the n over n, and then the trace of rho to the n plus 1 minus 1. Now, you know that trace of rho is equal to 1, and that means that trace of rho to the n is actually less than 1, because you have a sum of numbers which are all less than 1, and you raise them to a higher power. So that's automatically bounded. So you know that what's in parentheses here is bounded, and that immediately tells you that this series is absolutely convergent in the unit disk with radius 1. In fact, not only is it absolutely convergent, I can calculate what it is because I can resum this series. This is just really the series of a log. So when I resum, I get this expression here. Now, what is the analytic structure of this function as a function of z? Well, first of all, there is a singularity when z is 1. So there is a branch cut starting at 1, which I can take on the positive axis. So there is a branch cut going from 1 to infinity. Now, rho has eigenvalues which are all smaller than 1. And that means there are branch points at z is equal to 1 over these p alphas that were the eigenvalues of rho. But since p alpha is less than 1, 1 over p alpha is larger than 1. So in fact, what you have is a sequence of branch cuts starting at 1 and then going all the way out to infinity. In other words, this function defined this way should be analytic in the complex plane, except for a branch cut or a multiple branch cut going from 1 to plus infinity. So knowing that, then the function which was defined by which was defined by a series, which is convergent in the unit disk, actually can be analytically continued in z to the entire complex plane, except for this branch cut from 1 to infinity. Okay, this is by standard analytic continuation. This function is given by a series convergent in an open set, and now by standard analytic continuation, I can continue it throughout the complex plane. And in fact, from this, we know that there are no singularities when the real part of z is less than 0, because that's away from these branch cuts. And so now you just look at this formula and you take z going to minus infinity. if you take z going to minus infinity, the argument of the law collapses to being just rho. And we get our formula. So to summarize, here we've only used the values of the Renyi entropies for integer n, put them in a generating function, which is convergent in a unit disk. And then we know that it can be analytically continued throughout, and in particular to z going to minus infinity, and that limit gives you the von Neumann entropy. Any questions? So
yes,
this is,
I have a question, but I'm guessing you probably on your next slide maybe going to answer it, which is that does this is this guaranteed to avoid the possible ambiguities that you would have via the other methods, simply because you're is the reason that it avoids that, if it does, because in fact you never do anything funny with the integers, as it were. You simply avoid all of that integer character of the Renyi entropies in your continuation.
Yep. That is indeed the case. So this is unique, right? If I have the Renyi entropies given, or trace of rho to the n, then this G is unique. It's defined uniquely in the unit disk by a convergent series. So now, now I know that, so if you have an analytic function defined in the unit disk, that continues uniquely, except of course for branch cuts and poles that you might find. But otherwise, it's uniquely defined by this expression.
Quick follow-up question. One could imagine making a different generating function built out of the same objects.
Yes.
And then given that definition, one would then have some nice unique continuation along the lines, but it would be a different function. Are they guaranteed to give the same entropy in the appropriate limit?
Well, I think so. If you cook up something that, you know, is analytic and well-defined, I mean, here we simply show, right, by taking the limit z goes to I mean, we define this thing, we evaluate it by summing the series. This is an expression that's convergent when in the unit disk. You analyze its singularities in the plane. There are no singularities in the left half plane. And then you show, just by basically substitution, that its limit gives you this von Neumann entropy, which is well defined. I mean, that you know that it's well defined. I think maybe what you're asking is, suppose I give you a set of values for trace of rho to the n, and I didn't know this came from a density matrix. Okay, you could give me all, I mean, not every sequence of numbers for trace of rho to the n would come from a density matrix. In particular, they have this ordered property, right? That trace of rho to the n is less than trace of rho to the n prime if n is greater than n prime. So if you were to violate that, then of course all bets are off. So I'm assuming here that we know that these values of trace of rho to the n came from a genuine density matrix. And then I think the result is unique, yes.
Yes, thank you.
Does that make sense?
Yes, it seems very nice. I was thinking something more simple-minded, which is that if I messed around with what I meant by generating function and maybe use some different function of z and that sum or something, but probably then what I'll run afoul of is your nice convergent.
Yeah, I mean, you have to insist on starting with something that's convergent, right?
Yeah.
That's absolutely convergent, because that's the way you find out that this function is actually analytic in the unit disk. But once you've done that, and once you've shown that the analytic continuation does not involve any poles or cuts in the region you're interested in, then I think you're fine,
Yeah, it's very nice. Thanks.
Well, thank you. All right. Well,
can I add a question?
Yes.
Yeah. Do you think that this G is a function of Z may have some other interesting physical meanings as entropy or some sort of concept similar to entropy for other values of Z?
Yeah, well, no, I don't really have a good guess at this point. I mean, your question could be, could I view G, the entire generating function, as a measure, of entanglement? And I think the answer to that is yes, because in fact it interpolates in a way between the von Neumann entropy at infinity and then in its expansion, the Renyi entropy. So, but it would itself would not satisfy additivity or subadditivity properties. That I think.
So you're saying it does not, or I mean,
well, it's not an entropy in the usual sense, or maybe more accurately, I don't really know whether it has a direct physical meaning.
Okay, fine, that's fine. Thank you.
Sorry, actually, so I had a question like that myself, and where I was going, Ishak, maybe Eric has a comment. There's a way of thinking about the Renyi entropy as a quench in some system where you evaluate, you think of it as a difference between free energies at different temperatures in some sense that I won't define now to save time. And so I was just wondering if G might have a meaning in that quench language, which you probably know, Eric.
No, I don't actually.
Oh, okay.
That would be very interesting. Yeah. No,
it seems like it's begging to make that connection. So maybe I'll tell you a little bit about it after.
Okay. Yeah. Okay. No, good. Interesting questions. Thank you.
Okay. Thanks.
Okay, so now let's apply this. Let's see how this works, right? I claim that we have another way of evaluating things. So let's see how this works. So first of all, the one interval case. Now, of course, this case was completely trivial in the original replica method. So let's see what you have to do here to reproduce that. So the formula for the Renyi entropies was given by, remember, this combination of the exponential of y, and then 1 over n minus n, but here we have to shift by 1 because of this entry here. And y is still this combination that I'm just going to abbreviate. Now, I don't know what to do with this exponential in y over n plus 1. So the best thing I know how to do is to expand it in a power series. So here it is, I expand it in a power series. And that gives rise to a series in J. So J here is the expansion of in y over n plus 1. Okay. Now this is not exactly a series you know how to do either. So let's interchange the orders of summations. Now we can do that because these series are actually absolutely convergent. And for y positive. And so here is the series. And so I regrouped it in terms of a function f, which we will encounter frequently. So this is again a function whose radius of convergence by this series is 1, essentially. Okay. So now what we want is we want to analytically continue this to z going to minus infinity. So we need to work because this function is actually only defined by a series convergent in the unit disk. So how do we do that? Well, you can use partial fraction expansion. And when you do that, then in fact, you know how to sum both contributions because you have sums of the type z to the n over n to some power. And those functions are so-called polylogs. So the polylog Li sub s of z is defined as a sum of z to the n over n to the s. These are extremely well-studied functions. And you can compute this out, and here is fj of z. So it's the sum of polylogs. Okay, Well, we've now shifted the problem of analytically continuing in Z of this function f to that of the polylogs, but that's actually very well known. And the asymptotic expansion for Z going to minus infinity is actually given by what we in physics would call the Sommerfeld expansion. If you've ever taught stat mech, then this will be familiar. This is how you get the low temperature expansion, for example, of Fermi-Dirac or Bose-Einstein. And so the formula is a bit complicated, but not fundamentally difficult. So Li sub s is given by an infinite sum of inverse powers of the log of minus z. And so, so if s is positive here, then the leading term is some positive power of the log, but then you get lesser and lesser powers of log. And in fact, if s is an integer, this infinite series truncates because at some point, the argument of the gamma function is negative, a negative integer, and then that's equal to 0. So it's actually only a finite sum. And you can evaluate this in the limit when z goes to infinity because the correction terms are of order 1 over z and higher. And so the evaluation of this is that f of j of z is j minus the log of minus z and then plus inverse powers of z. And so then as a result, g of z is this log, and then this combination, this you can throw away at the end. And now you can see that you can actually resum because y to the j and then 1 over j minus 1 factorial, that's just an exponential. And then here the log of minus z, that comes out as well. And so what you find is in the limit, you find just 2y. This 2y comes from taking the log of y here, of e to the minus y here. So that gives you some proportion to y, and then you need to calculate the rest and make sure, but this gives you exactly this result. So first of all, what we learn is that, yes, you can reproduce the one interval result. That's good, because if we couldn't do that, really not be in business. However, you also do learn that the steps needed are not trivial to do this. Now, fortunately, for the two interval case, the steps needed are essentially the same. They're not fundamentally more complicated. And so let me explain briefly how this calculation goes. I know you all want to see what the elections are doing, so I don't want to take too much time. But, well, probably nothing will happen really today. But so recall that the trace of rho to the n was the same prefactor that we had in the one interval case, and then this complicated function here. So the essence is really this complicated function. The rest is rather simple. So I will now take the somewhat simplified generating function where I strip off the factors that don't really matter. So the n and the x to the alpha and the 4 to the alpha, just strip it away. And so we're left with this expression where this exponential is again the prefactor. And then here is the insertion of this sum. Now, again, I don't know what to do with this y over n except for expanding, so I'll expand again. So here's now the expansion. Now here, I have to deal with this sum, this finite sum for each n, and this n is summed over. And Calabrese, Cardi, and Tani actually had a trick for this, and that is to expand the function u over the sine of u. Remember, this is raised to a power 2 alpha. Alpha is a real number, positive, but very little known about it otherwise. So it's a general number, it's not an integer. And so you can actually expand this in powers of u. This is a very convergent series in u, even in u. And then the coefficients of polynomials of degree k in alpha. The radius of convergence is pi, and the reason is that that's the first singularity of the sign that you encounter. So this expansion was used by these guys as well, and we're going to use it also here. So when you do it, you get a, well, somewhat more complicated expression, but at least now you have something that sums from 1 over n, and that you know how to represent as an integral. So this can be represented, I think you all know this kind of thing, right? You have a power here, you can represent it essentially in terms of a gamma function integral. And to get the right powers of 2k, you write this as a derivative of order 2k of this sum. So this is still a sum to a finite integer, but this sum can actually be done exactly and gives you something like 1 minus e to the minus n pi t over the same thing where n is equal to 1. So, okay, I don't want to go through all the details I given here. And so you can get this reasonably nice integral expression for the generating function as this integral over t, some derivatives with respect to t, and then this ratio of this function h over this Bose-Einstein type density factor. So h involves these similar sums to what we had before. And again, these sums over n I can actually do by partial fraction decomposition in n, as we did for the one interval case. Then the remaining summations can be done in terms of polylogs. And I'm going to spare you the details. It's not complicated to work it out, but you have to work on it a bit. By the same type of argument that we used in the same expansion of the polylogs, you actually find that the limit of hk is minus pi t plus 1 over z. Now, I have to say immediately that while the original summation formula was nicely convergent in k, okay, here, this limit introduces a non-uniformity in k. So while here you had many negative powers of k in n, this is no longer true here. And this fact will come back to haunt us in a few minutes. So now, can we recover this formula by Calabresi, Cardi, and Tani? Well, so I claim this limit somewhat naively when z goes to minus infinity. H then reduces to just t. And actually, with a little bit of work, you can carry out this limit and you find this series, which involves the Riemann zeta function evaluated at 2 alpha minus 2k. Now, this series, unfortunately, is only asymptotic. And so to resum it, you need some kind of Borel resummation. We believe there's probably a way of getting around this, and we're working on that. But for the moment, that's what we have. So then once you know this sum, I can use the functional equation for zeta relating zeta of z to zeta of 1 minus z and use an integral representation for it. I'm again going to spare you all the details. And so you find an expression that you can in fact evaluate and you find the same result. So we recover, in the 2 interval case, we recover the expressions of Calabresi, Cardi, and Tani. Okay, well, that's good. Now, I announced earlier that in fact one can, in addition to doing analytical calculations, you can actually do numerical calculations as well. Let me show you how that works. So in the replica method, numerical calculations, that's a bit, you know, it's not that easy to imagine because you would basically have to have some numerical way of analytically continuing. That's pretty tricky, but nonetheless has been done by a method which is called rational interpolation by these authors. And they find results that in fact we can compare with. So let me show you how this works. So our method provides a way around this analytic continuation the following way. Here we had an expression which was only convergent in the unit disk for Z, and which gave this expression. But now let's change variables by making a Möbius transformation. So let's set Z equal to W over W minus 1. This is easily worked out. After all, this is a Möbius transformation itself. And so what you get is G of Z of rho is the trace of the log of, the trace of rho times the log of 1 minus W times 1 minus rho. Or if you expand it in powers of W now, it's this expression. Now, this expression you need when Z goes to minus infinity. That actually means that W goes to 1 from below. W going to 1 is something that is accessible here at the boundary of its radius of convergence. In other words, this series in terms of W, the coefficients are given by the trace of rho 1 minus rho to the n. This number is positive and smaller than 1 because the trace of rho is 1. And so actually the radius of convergence of this is 1. So taking W to 1 is taking this series, which is valid in the entire unit disk, just to the boundary of the disk. And so these coefficients can be calculated in terms of Renyi entropies just by using the binomial expansion. And so numerically then, what we need to do is to evaluate, we need to have available the trace of rho to the n, as we did before, the Renyi entropies. And then by this binomial expansion, we have the coefficients of this series. You compute it numerically, and then let W go to 1. In the best cases, you just set W equal to 1, actually. So how does this work? Well, we've done this for the case of two disjoint intervals in the limit where x is small. So this is the case where we have the analytic expression available from Calabrese, Cardi, and Tani. And so the plot here is as a function of x, the entropy is plotted for different values of this number alpha. This number alpha of interest is somewhere between 0 and 1 typically, and that's what we have done. And so the solid lines are given by this exact result that we had, and the dots are given by our numerical interpolation or numerical evaluation. So that works pretty well. And on the next plot, we've done the other way around. So we plot alpha versus S versus alpha for different values of x. So x is reasonably small. And again, you see that this gives satisfactory results. We've also done some other stuff where we knew that exact results were available. You can do the one interval, but actually put the system at finite temperature. And there are exact results known by these authors. In fact, some very recent of just last year. And so this is plotted in a solid line. And then the dots are in from our numerical method. So that works pretty well too. And then the final one is that, well, in the case of a compactified boson on a circle, there are results known for the decompactification limit by these people. And so again, we compared as a function of eta. Eta here is the square of the compactification. And you again, this actually work. So now the question is, can we actually do it? Namely, there is in fact an exact formula known for the two interval solution, not just in the limit when the two intervals are small compared to their separation, but in general. So the formula is again due to Calabrese, Cardi, and Tani in these beautiful papers. So there is a prefactor, and then there is again this F, But now here is the full formula for this F. So the full formula is given by a ratio of Riemann theta functions, and there's a bar missing here. Sorry about that. So the Riemann theta function is 1 for the rank n-1, where n is n here. So the rank depends on the power of rho. And it's given by this familiar formula. You sum over all points in Z to the n1, this matrix omega. And then the formula is given by taking the product of these thetas for omega times eta and omega divided by eta, and then just omega here. Now, what is omega? Well, actually, omega is an awful matrix. R and S run from 1 to n-1. You see these sines, these cosines, then so you see some hypergeometric functions, evaluate them k over n. And A is the compactification radius square. Well, we wish we knew how to do this, but at this point, it is unknown. I mean, we can write down the generating function, of course, as we did before. But how does one simplify this as a function of Z so that we can see the analytic continuation? At this point, numerical results are available. We've done some of them, but there is nothing to compare because there is nothing in terms of the von Neumann entropy that people have succeeded in doing. So at this point, we're a bit stuck at this point. So I'm out of time, so let me give you a summary and outlook. So I hope I've convinced you that we have an alternative way for extracting the Neumann entropy from the Renyi entropies in terms of a generating function, convergent in the unit disk, and which always admits this analytic continuation. Also, we have been able to do some numerical approximations. But we clearly need better methods to simplify the generating function. We don't know how to do this for general reasons of the intervals. And even in the case of the two interval case, we still have to go through this analytic, through this asymptotic series and do a Borel resummation. It would be much nicer if we could avoid that. And at this point, we're working on that, but we're not quite there yet. I should just say that for the case of multiple intervals, two intervals with higher order, people have actually looked at precision calculations involving higher rank data functions very recently. So maybe there is some hope there. And finally, I'm just going to mention that there is a way of getting to the von Neumann entropy, which is actually to take not rho to an integer power, but rho to 1 over n. Also continuing to n is equal to 1, but in a sense from below. And this has come up in orbifold calculations, where basically, instead of having several copies, you actually mod out by n. And this was used in a recent paper by Witten on the Rindler horizon. Our methods clearly don't apply to this. And so it would be interesting to see whether an alternative method could be found that actually applies here. Okay, so I want to stop here and thank you very much. Thank you.
That was very nice. Are there questions from the audience?
I have a small question, and maybe it's unreasonable, but you can tell me. So I was wondering whether you have been thinking about the relation of this very nice method for computing the von Neumann entropy with regards to these computations regarding the replica trick in gravity, where they take this these boundaries and define these wormholes that are connected in some interesting way. I mean, do you have any intuition? Maybe not, but if you have any intuition regarding how might that look like from this perspective?
You're referring basically to these calculations by Maldacena and Lefkowitz, where you take a cone of an opening angle and then let this opening angle go to whatever, 2 pi or something. Is that what you mean?
Yes. I mean, I was referring more to these new papers where they look at the page curve and so on, but it's essentially the same thing, at least my understanding of it.
Right. So this is basically from the holographic side, how you compute this.
Yes, exactly.
No, we have actually not tried to do that. I think in those cases, usually, because you have a continuous variable sort of to start with, right? The deficit angle is in some sense a continuous variable. I think the analytic continuation is always sort of more reliable because it's geometrical. You don't start from the Renyi entropies there, right? You actually start from a geometrical formula with a deficit angle. You put in an operator, it creates a deficit angle there, but the magnitude of that deficit angle is sort of by construction a real number.
Yes, that's true. That's true. Yeah, I think I was also referring to this fact that these other calculations in which you have you create several copies of the spacetime, and then you have let's say you have 2 boundaries, and then you have when you start doing the replicas, you have different ways of connecting those 2 boundaries when you do the replica trick, and one contribution comes from each boundary being like connected to itself. And then there's a wormhole contribution that connected 2 boundaries asymptotically, like this. And in that case, the replica trick, from that perspective, the replica trick has this additional structure. So I was wondering whether you have maybe thought something about that from this perspective. But yeah, I agree with what you're saying about that.
Right. Yeah, I think it's, I mean, what you're referring to is a very interesting problem. But I think in some sense, you don't need this machinery here because you have a continuous variable available.
Okay. Thank you.
Sure.
Any other questions?
Eric, this was very nice. And
thank you, Itzhak.
You know, you were in the previous slide, you were saying that you feel stuck because you don't have anything to compare to. But it seems to me you are a little bit ahead rather than being stuck.
Well, that's usually what happens, right? You're ahead, but then right. I basically what I mean is I don't know how to deal with such functions. I mean, this is really amazing that they were able to compute it, in fact, in the first place.
Sure. I just want to give you some encouragement, that's all.
You seem to be like in King's College, Cambridge or something.
Actually, it is Yale University.
Yale University, I see, okay. Right.
I actually had an interesting coincidence I haven't had before, which is that, so some of my students, of course, use some standard background that they got from somewhere. And one of them is, I think, the Golden Gate Bridge or something. And,
well, that's a popular one.
One day, more than one of them had the Golden Gate Bridge, sort of saying that clearly you're not social distancing, you're sitting in exactly the same place.
Yeah, that's right. Let's see what I can, I guess I use some standard ones. Well, I use some ones that are actually pictures usually.
Right, yeah.
But now I don't quite see how I get my Zoom thing again. Let's see. Yeah, here's one I sort of like. You know. Especially from Southern California, when there was a heat wave, you know, that worked pretty well, actually.